Hello everyone, I am excited to present our research on acute lymphoblastic leukemia diagnosis and subtype segmentation in blood smears using CNN and UNet. This work was conducted collaboratively with a dedicated team of researchers. In this presentation, we will talk about abstract, introduction, literature review, methodology, proposed methodology, model architecture, result, discussion, conclusion, and references. This study aims to address the challenges in diagnosing all by proposing a novel approach using convolutional neural networks and UNet models. The goal is to enhance accuracy, reduce dependency on invasive procedures, and provide a faster diagnostic solution. We combined a UNet model for image segmentation with customized CNN, MobileNet v2, Inception v3, ResNet 50, NASNet for feature extraction. Among the architectures tested, customized CNN achieved the best performance, with results showing 99.31% training accuracy, 97.09% validation accuracy, and 98% test accuracy. Acute lymphoblastic leukemia, or ALL, is a severe blood cancer that primarily affects children and requires precise early diagnosis. Current diagnostic methods rely heavily on peripheral blood smear analysis, which, while essential, depends on manual interpretation. This often leads to misdiagnoses due to subtle visual indicators. Our research aims to solve this problem by introducing a deep learning-based approach that automates the diagnosis and classification process, making it faster, more accurate, and less invasive. The key challenge we address is the high error rate in manual blood smear analysis, which delays or misdirects treatment. Our goal was to develop a robust model combining UNet for segmentation and CNN architectures for feature extraction, enabling the accurate identification and classification of all subtypes. We also sought to benchmark the performance of different CNN models to identify the most effective one. We explored existing studies that utilized CNNs for leukemia diagnosis. Key findings include Kuzai et al., who used BGG19 for all detection, Das et al., who combined ResNet 18 with orthogonal softmax for improved performance, Hou et al., who implemented a hybrid transfer learning XGB model for enhanced classification. However, these approaches often lacked comprehensive segmentation and struggled with subtype classification. Our research bridges these gaps by integrating segmentation with high accuracy classification. Our approach began with data collection. We used a publicly available dataset of 3,256 blood smear images from 89 patients, obtained from Telekani Hospital, Iran. The dataset includes benign samples for 3 malignant subtypes: early pre-B, pre-B, and pro-B. Pre-processing involved resizing images to 224 x 224 pixels and augmenting them through rotating contrast adjustments and segmentation using HSV color space. For modeling, we employed UNet for segmentation, isolating key regions in the blood smear images, CNN architectures for feature extraction and classification, including DenseNet 201, MobileNet v2, and ResNet 50. This is our methodology workflow. First we import our dataset, then we apply various data augmentation like rotation, flipping, cropping, cutout, contrast and brightness adjustment. Then we apply data segmentation using UNet model. Then we apply customized CNN, Inception V3, ResNet 50, NASNet model. Then we use SGD Adam RMS as optimizer. Use precision recall F1 score as performance measure. Let's take a closer look at the customized CNN model architecture. The deep learning model designed for image recognition tasks has a customized CNN architecture. The model includes an input layer specifically for RGB images of size 224 into 224. It also has convolutional layers for feature extraction, pooling layers for dimensionality reduction, dropout layers to prevent overfitting, and dense layers for classification. The array allele activation, batch normalization, and dropout techniques are employed in the model's architecture to improve its performance and generalization. There are 200 filters in the first convolutional layer, 150 filters in the second convolutional layer, and so on down to 50 filters in the fourth convolutional layer, with each layer 3x3 kernel sizes. The first and second layers are max pooling layers with a pool of size of 4x4, applied twice with a rate of 0.8 after the first and third convolutional layers to prevent overfitting. This layer transforms the 2D arrays from the previous layers into a 1D array, preparing it for the fully connected layers. After the convolutional layers, the architecture includes a dense layer with 256 units and array allele activation, followed by batch normalization for stabilization, activation, and a dropout rate of 0.8 to reduce overfitting. The architecture involves a contracting functional block or encoder and a transformational functional block decoder. The contracting passage looks like a simple CNN architectural design that comprises several convolutional and pooling layers. Each contracting path block, like all the others, generally has 2 3x3 convolutions followed by a rectified linear unit, activation function, and max pooling with Windows subsampling size 2x2. The expensive path hub samples feature maps to the original input size, increases resolution, and recovers spatial information lost during downsampling. It uses upconvolutional layers to boost spatial resolution. Concatenation of contracting and expensive path feature maps provides extensive localization information. The last layer is the most important layer as follows. It consists of a 1x1 convolutional layer and a softmax activation function with an output of the segmentation mask composed of pixel-wise classification probabilities from each class. At the end of the network channels present a number equals a number of segmentation classes. These are the results. In model MobileNet V2, test accuracy is 97%, Inception V3, the test accuracy is 77%, ResNet 50, the test accuracy is 97%, in NASNet, the test accuracy is 81%, and customized CNN has the most test accuracy, 98%. In this scenario, the first figure shows the training and validation accuracy over epochs. Over epoch, both accuracy are improved. Second figure shows the training and validation loss over epochs. Our findings highlight the potential of combining segmentation and classification for accurate all diagnosis. The UNET model effectively segmented critical features, while the customized CNN ensured reliable classification of all subtypes. Customized CNN and ResNet 50. Best performers with highest classification scores effective for real-life applications. MobileNet V2 balanced performance with 97% precision, recall and F1 score, noted for computational efficiency. Inception V3 and NASNet has lower matrices, require refinements, hyperparameter tuning or extended training. In conclusion, our research demonstrates that this study provides a comprehensive evaluation of deep learning architectures for image classification, emphasizing the significance of model selection and optimization for achieving high accuracy and generalization. The customized CNN emerges as the most effective model, achieving 99% accuracy and demonstrating its suitability for deployment in real-world scenarios due to low error rates and robust performance. MobileNet V2 stands out for its computational efficiency and applicability in resource-constrained environments, with 98% validation accuracy and high precision. We believe this work is a step toward integrating AI into clinical workflows, enhancing diagnostic precision while reducing healthcare burdens. This is some paper that we use as a reference. I would like to thank my co-authors and collaborators for their contributions to this work. Thank you all for your attention.